Good evening. Well, we have chosen a topic today that I would not say is particularly difficult, but that has changed surprisingly over the past few years. When Sarah a little later and I a little earlier started studying astronomy, there was nothing but stars in space. We knew that the cosmos was the stars, and they would tell us everything. In fact, there was nothing else to study. What seems important to us, planets, satellites, some meteorites, all this is such a small addition to the stellar population of the universe. Well, like a pinch of salt, yes, here, no more than that. But the situation has changed dramatically. Now we look at the population of our cosmos with horror. 2/3 or even 3/4 are not God. Well, in general, no one knows what it is, under the conventional name of dark energy. This is something that has the property of anti-gravity, a fantastic thing which, as it turns out, is realized in nature. Nobody will tell you anything about it, but it's there. We can feel it in the movement of galaxies. There's another quarter of the population of the universe, dark matter. We possess some knowledge regarding it. We comprehend that it aligns with the overarching principles of physics. Our understanding of dark energy is limited, while we are aware that dark matter is an unidentified elementary particle. Its mysterious nature stems from the fact that no lab on Earth has been able to detect it, yet it is perceivable in the cosmos. Scientists have been aware of these enigmatic particles for over 50 years. They, at the very least, exhibit the typical characteristics of gravity, for which we are thankful. However, we have yet to unveil their other properties and devise methods to capture and study them using laboratory instruments, although numerous physicists are actively engaged in this pursuit. But this does not annoy us much. We'll find a way to study them. Where are the stars? Well, it would seem that this is the population of space, although 5% of the universe in terms of energy and mass, but at least we know what it's made of. Protons, neutrons, electrons, something we experienced back in school as a medium familiar to scientists. But it turns out it's mostly gas. A medium almost invisible, hard to see. Even the coolest telescopes can't often capture it. It's very hot gas between galaxies. And there's only 5% of the universe. 5%. That's about, half a percent of the universe. You could forget about it and say that stars aren't worth studying at all because they're a tiny fraction. Nevertheless, when we look up at the sky, we see nothing but stars. And a telescope looking at the sky also sees nothing but stars. So whether we want to or not, we have to study the universe by looking at the stars, because there are practically no other sources of information. And they tell us a lot about the evolution of matter, about the evolution of ourselves, about the evolution of any pinch of salt in the guise of planets and biosphere on them. Well, in and of themselves, they're certainly curious from the point of view of physics, to understand what's going on there. Looking at the sky with the naked eye, we see stars. Somebody may say, well guys, you have modern equipment, a telescope, take it in your hands, and you will see something else in the universe. We take the telescope. We see more stars, but we don't see anything else but stars. And if we try really hard, we can see more stars, even more stars. This is the world's biggest telescope showing us a picture like this. A tiny patch of starry sky photographed by a telescope, just a little bit bigger than this audience, 8 meters in diameter. Well, that's about right, isn't it? The largest telescope has a mirror like this. Nothing but stars again. So you can't go anywhere to study the world on the basis of stars after all. And as it turns out, they were born in the past, were born in the not-so-distant past, are born today, and probably will be born in the universe for quite a long time. So first of all, we need to understand where they come from, how they are formed, from what environment these dense, beautiful, natural thermonuclear reactors are released that make the motion of the universe, the movement of matter in the world. This is in fact the only source of energy in the universe today, well, almost the only one. It is starlight. We have stars of different generations in front of us. Very old ones, over 10 billion years old since their creation. Our sun, like many other stars, is a middle-aged star, often referred to as teenagers or youngsters. It is still in the process of being formed, like babies inside a protective cocoon of matter. In this discussion, I will touch upon the origins of stars and the fascinating process of their birth. The first half of our discussion will be dedicated to exploring the origins of stars, dissecting the intricate journey they undertake, what we think we've understood so far. And the second part will be about how they evolve and what they turn into at the end of their lives. So there's a theoretical foundation. Physicists have long thought about how stars arise in nature. It was clear that since something gives off energy, it must eventually die. Well, heat. There's never an infinite amount of energy anywhere. So physicists realized that they had to figure out how to reproduce stellar matter. And quite a long time ago they discovered, besides stars, also rarefied gas. Then we realized dust, small solid particles. Here's a dust cloud on the background of a hot gas cloud. At first these, what our teachers referred to as nebulae, as they possess a vague appearance, albeit often exhibiting a highly intricate structure, initially failed to grab our attention. However, over time, we became convinced that they offered an explanation for the birth of stars. This ethereal matter must somehow transform into denser entities of colossal mass. But where does this matter emerge from? We witness it during every solar eclipse in the form of a corona enfolding our sun. A mere glimpse at the solar corona allows one to comprehend that stars gradually lose a portion of their substance, which disperses. The coronae of individual stars intermingle, resulting in the phenomenon known as the stellar wind. Eventually, exceedingly rarefied matter accumulates in the interstellar expanse. Origin of stars. When observing a visual representation, one cannot ascertain that the solar corona comprises rarefied gas. It possesses such tangibility that it appears as if one could simply cut through it with a knife. I dare claim that the ultra-high vacuum scientists have managed to create within their laboratories is referred to as the ultra-high vacuum for the precise reason that it is highly improbable we will ever achieve the creation of an even more rarefied medium. Its density aligns with that of regions within the solar corona, with approximately 1 billion atoms packed into a cubic centimeter. Well, chemists and physicists realize it's a very rarefied environment because we have billions upon billions of atoms right here in the air, in this cubic centimeter. It's very difficult to pump a vessel down to like 1 billion atoms in a cubic centimeter. And for nature, it's a very tangible medium. Then, as it leaves the neighborhood of the star, it becomes less and less dense, and it seems to disappear completely. Stars are formed from matter that is out of sight. When the sun loses its matter, it doesn't have a significant impact on its lifespan. Thus, this gas plays a role in the formation of stars. The sun will lose about 0.1% of its mass at the end of its life, an insignificant amount. But at the end of its life, the sun will start ejecting matter dramatically. This particular picture displays a violent eruption of matter, resembling the behavior of this star. At one point in time, this star, a star that resembles our sun, almost indistinguishable in mass. However, this star is older, with an age of around 10 billion years compared to our sun's 5 billion years. As it nears the end of its lifespan, it will leave behind a small core that contains approximately half of its original mass. The remaining half of the star's mass is rapidly lost within a span of about 10 million years, spewing it out intensely in all directions. We will talk about this more when we talk about the evolution of stars. We will talk about the cause of this phenomenon. Now, as you can see, half of the mass of the star returns back into space, back into the interstellar medium. These are what we call planetary nebulae. It's an unfortunate name, and it's been around since astronomers didn't have good telescopes. Looking at such an object from afar in a poor telescope, you see some kind of blot in the sky, a foggy disk, shaggy, and something that resembles the disk of a distant planet. In fact, this is a planetary nebula. It's not a planet-related environment, it's the last stages of a star's life. It looks very beautiful in the modern photographs that the Hubble Space Telescope gets, and for that, we're very grateful. On the one hand, we're now admiring these pictures. But unfortunately, no, I'm kidding. Not unfortunately, but fortunately for scientists, these planetary nebulae cannot yet be explained. Their shape is so complex that we can't understand how a spherical star, all ball stars, you look at them like a billiard ball, all the same on all sides. How do they organize in space around them in such a complex pattern? Today, you will also have the opportunity to observe images of planetary nebulae. These celestial phenomena exhibit incredibly intricate and complex shapes. It is perplexing to contemplate how a star, which initially appears as smooth as a billiard ball, can expel matter in specific directions but not in others. Moreover, you will encounter numerous awe-inspiring forms of planetary nebulae. Fortunately for aspiring researchers, the physics behind these phenomena remains enigmatic, allowing for ample opportunity for investigation. Interstellar gas and its properties. This gas is gradually filling the space between the stars, and more of it is being added, not so harmlessly lost to the stars, I'd say. Here we have before us the well-known constellation of Orion. And by the way, here's the giant cluster of gas in which stars are forming before our eyes. Here's Alpha, Orion's brightest star, Betelgeuse. It's in the next 10 or so, maybe not, the next 100,000 years or so, that's a blink of an eye in the realm of astronomy, that the event we refer to as stellar gas loss sheds light on the various ways stars can discharge gas. To form a colossal cluster of matter in which new stars can emerge, it's evident that the amount of gas expelled by the Sun and its celestial counterparts, similar to our very own Sun, would be insufficient. We require a more substantial influx, one that we observe during the demise of massive stars. Take a moment to observe the substantial amount of gas that exists in the vast expanse between the stars. It appears as though there are no stars at all, doesn't it? However, this perception is achieved through a remarkable photography technique. By placing a light filter in front of the telescope, only the light emitted from the gas is accentuated, while the brightness from specific stars is deliberately diminished. In this way, the space seems to be solely saturated with gas. Through this process, we slowly begin to comprehend how this fiercely diffused medium can eventually condense into individual, compact masses known as stars. You see, the majority of the gas emits a luminous glow owing to its high temperature and radiation, akin to any other hot object. This tremendous heat is acquired as the gas is emitted from the innermost regions or surface of a star. Subsequently, it gradually loses its intensity as it cools down. And as it cools, it starts to shrink. The thing is, there are no solid walls in space, no vessels in which the gas is enclosed. If some region of interstellar gas cooled down, the pressure in it decreased, and the surrounding hot, dense, high-pressure gas begins to compress it. It gets compressed and becomes more and more dense. Notice right here, dark, dense, seemingly invisible clouds. Here are the tiny ones here. We see a low-visibility dark blob. It's actually much more massive than all the surrounding gas because it's already denser. Interstellar gas possesses a remarkable property that appears paradoxical to us. When we compress gas using a hand pump to inflate a bicycle tire, almost everyone knows how to do it. This process causes the pump to heat up in our hand. Why? We compress the gas and increase its internal energy, so it gets hotter. But interstellar gas, although it's also a gas, under these conditions behaves differently. The more you compress it, the faster it cools down. To cool down, the gas particles have to collide with each other, excite the electrons to higher energy levels, and then dump the excess energy in the form of infrared radiation. So by compressing the gas, you not only compact it, but also make it cool down a little bit. And once it cools down, it lowers its pressure, making it even easier to compress further. This is called thermal instability in the interstellar medium. Studying interstellar gas presents a challenge because it is rarely heated to a temperature high enough to emit visible light. As it cools down, it becomes invisible to optical instruments. However, this does not mean it cannot be detected by other devices. The majority of interstellar gas is composed of hydrogen, which accounts for 90% of its composition. Additionally, helium makes up 10% of the gas, while other substances are present in very small quantities. Hydrogen, consisting of one proton and one electron, is the primary component of interstellar gas. Surprisingly, both the proton and electron have a magnetic moment resembling tiny magnets. This means they can be oriented in either a parallel or anti-parallel manner to each other. When they are oriented parallel, the energy of their interaction, like two magnets repelling, is a little bit more. When they are anti-parallel, the energy of their interaction is a little bit less. So, the flipping of the electron's spin from one orientation to the other causes the hydrogen atom to release excess energy. It takes the form of an electromagnetic wave known as a radio wave. These waves have a length of 21 centimeters. This fortunate circumstance allows us to identify the presence of interstellar gas. The composition of this gas is primarily hydrogen, making up around 90% regardless of its temperature. However, it is more preferable for the gas to be cold and not ionized, existing in its atomic state. Radio telescopes have been crucial tools since the early 1950s for examining and detecting the interstellar medium. Nonetheless, there are other instruments available for this purpose. Studying interstellar gas. Before you, there are 4 complete star maps that provide an overview of the entire celestial sky. Similar to geographical maps that depict the Earth, these unfolded maps portray the vast expanse of the sky. Each of them is obtained in a certain range of radiation. The optical telescope photographed the whole sky, showing the band of the Milky Way. Black veins on it indicate that cold gas can be seen against the background of hot gas. This is exactly the same line, 21 centimeters long. It has its frequency written on it, the hydrogen emission line. In our terminology, cold hydrogen is referred to as H1, Hy. H2, H secondum, represents ionized hydrogen. As you can see, along the band of the Milky Way is the largest cluster of cold interstellar gas. And this is hotter, ionized hydrogen. It too lies in the plane of the galaxy, compressed to where gravity pushes it against the galactic plane. And here is carbon monoxide, a molecule, though not particularly complex. This is a very cold environment. These are the coldest regions of the interstellar medium, and they also lie in the plane of the Milky Way. In short, the medium from which, as we now know, stars are formed, is pressed against the plane of the galaxy because gravity drives it there, to the center, to the potential well, as a physicist would say, to the center of gravity of our stellar system. That's where it compacts, that's where it splits into separate fragments. Here's another wide-angle shot of the galaxy. The galaxy is actually flat, but in this wide-angle shot, it's so distorted across the sky that you can see it. We can immediately see the dark veins, previously known as dust bags, acting as barriers against the backdrop of stars. Hence, interstellar gas is not completely transparent as it absorbs light from distant sources. The gas itself does not possess significant light-absorbing properties. Consequently, the gas in this room does not impact our visual perception. However, if a dusty coal bag is disturbed, the resulting coal dust particles would immediately obstruct our ability to see each other. Even a mere few grams of dust would entirely absorb the light. This phenomenon is similar to what occurs in the interstellar medium. Within it, there exist solid particles which we commonly refer to as dust. These particles are minuscule in size. In terms of mass, they constitute approximately 1% of the interstellar medium. Nonetheless, they do not allow light to pass through them. As a result, these particles and the gas compact together towards the central plane of the galaxy. There are clouds where the interstellar dust is so densely packed that you can't see through them at all in the optical range. Of course, our predecessors, the astronomers of the 19th century, found it difficult to realize that it was here, where nothing could be seen, that new generations of stars are born. If you can't see anything there, how can you even understand what's going on? Today, we have the technique of infrared telescopes and radio telescopes, for which even such dense clouds become translucent or completely transparent. We quietly study their internal structure and see that it is there that stars are born. Until the 19th century, the process of star formation was not understood. Even in the middle of the 20th century, there were heated debates, especially in our country, about how stars are born. Maybe some of you remember the name of academician Victor Ambartsumian. No? You don't? He was Armenian. By the way, after he graduated from university, he worked briefly in St. Petersburg, in Leningrad. Yes, he graduated from Leningrad University. He became the head of the Armenian Astronomical School, the founder of the Bayrakhan Observatory, a very good mathematician. He even had his own original theory of the birth of stars from superdense matter of mysterious nature. We resisted this idea for a long time, trying to explain to him that nature forms stars in a different way. But he stood his ground, partly for publicity to highlight his observatory, but partly because we didn't have enough arguments back then. Really, how do you understand that in these cold clouds, like the famous Horsehead Nebula, that dark silhouette, anything at all is happening? If you can't see anything there, how can you even figure out what's going on? Little by little, we figured it out. First, we realized that the interstellar medium is not homogeneous. There are enormous variations in temperature and density, but the chemical composition is actually quite uniform. Astronomers today distinguish three characteristic types of interstellar medium: star formation and the interstellar medium. Little by little, we figured it out. First, we realized that the interstellar medium is not homogeneous. There are extremely large variations in temperature and density, though its chemical composition is actually quite uniform. Astronomers today distinguish three characteristic types of interstellar medium. Cold. Since the temperature is low, molecules are able to form in this environment, because at high temperatures they tend to dissociate easily. They get destroyed. But at low temperatures, these molecules are preserved. One example is hydrogen, in the form of the H2 molecule, which exists in what scientists call molecular clouds. Additionally, there exists a medium composed of individual atomic hydrogen. Physicists sometimes symbolize this as H0, while spectroscopists and chemists prefer H1. This medium is found at moderate temperatures where molecules are destroyed by heat, and the atoms remain separate, each with its own electrons, remaining neutral. Finally, there is hot gas, where H2 represents fully ionized hydrogen. This means that the electron and proton, the nucleus of the atom, exist independently of each other. In one region of space, you can observe all three forms of hydrogen. It's quite cold at this location. And here, just off-screen, there's a scorching star heating up a cold cloud with its rays. The intense heat prompts hot gas to rise, where it loses its molecular form, breaking down molecules. As the gas approaches the star, it reaches a temperature of around 8,000 to 10,000 Kelvin. Electrons break away from atoms, and the medium becomes ionized. So in a single region, you can find all three types. Which one of them is mostly responsible for star formation? The one where it's coldest. By the way, where it's coldest is also where the composition of the interstellar medium is most complex. Starting in the late 1930s, first with optical telescopes, and then with radio telescopes in different bands, centimeter, millimeter, we began to discover molecules more complex than hydrogen. This is the very beginning of the list. These are the most widely represented molecules in the interstellar medium. Today, that list includes about 200 different molecules. Some of the most complex ones have up to 13 atoms. It might not sound like much, but among them are even amino acids. Biologists interested in the search for life in the universe already say that the first steps in the evolution of life might take place not even on planets, but in the interstellar medium, forming the first protobiological molecules. Some amino acids, like glycine, and even fullerenes and carbon complexes. It is in this relatively cold environment, where molecules can form, that stars are born. Formation of the interstellar medium. Speaking of molecules, it's always a big challenge for nature to create molecules, even from the same atoms. Combining different atoms, carbon and oxygen or hydrogen and oxygen, is relatively easy. This is very important for star formation. Molecules play a big role. But to put two identical atoms together, for example, two hydrogen atoms into an H2 molecule, is very difficult for nature, because to bond, they need to shed excess energy. But how do you remove that energy if the atoms are identical? They can't decide which one is going to release it. When there are different atoms, it's always easier for them to solve this problem. This is where dust particles come in. They're few in number, but they're incredibly important. Just like a tiny catalytic converter in a car exhaust pipe, which transforms harmful gases into less harmful ones. A hydrogen atom sticks to a speck of dust. Though I've drawn it as a round sphere, it's really an aggregate with protrusions and an uneven surface. The atom wanders around it looking for a convenient place to settle, often on some bump where the electric potential is higher. There it sits and waits. Waiting for another atom to come along, that second atom also wanders, and eventually, in the most favorable spot, they meet. They bond, releasing their excess energy, which is absorbed by the dust particle itself. The dust gets a little bit warmer, emits infrared radiation, and the newly formed H2 molecule eventually detaches and flies off into space. This is important because at low temperatures, atoms can't radiate energy, but molecules can. Molecules can spin, vibrate, and change their internal energy states in many ways. They can release very low energy quanta, effectively serving as refrigerators in the interstellar medium. As molecules form, they cool the surrounding gas, allowing it to collapse further under gravity. Theory of star formation. The person who first demonstrated with formulas and physics in his hands the process of star formation was the famous English astrophysicist James Jeans. He did a lot of things in physics, radiation, gas dynamics, but he was the first to look at this process systematically. Imagine a gas medium. Its atoms have two competing properties. First, gravity pulls them together, attracting them. Second, temperature makes them want to fly freely and disperse. Which force will win? I'm going to show you literally two slides. If you don't like physics, don't pay attention to them, but for physicists, it makes perfect sense. In this scenario, a gas cloud faces two opposing forces, gravity and gas pressure. Gravity tries to compress the cloud. Gas pressure tries to expand it and make it vanish. These two forces are locked in constant competition. Whoever works faster wins. Either gravity will compress it more quickly, or gas pressure will disperse it faster. So, Jeans developed two formulas. One formula describes the speed of sound, the speed at which pressure waves can expand the cloud. The other describes the speed of gravitational contraction, how fast gravity can pull it in. From these, Jeans derived critical parameters, the size and mass of a cloud needed for gravity to win. He even gave it his initial J for Jeans. A big, massive cloud will be dominated by gravity. A small, lightweight cloud will be dominated by gas pressure and will disperse. So there's a critical threshold. For the interstellar clouds simply cannot form stars. They can't compress under their own gravity. Larger, more massive clouds can. But you see, everything depends on the parameters, temperature and density of the interstellar gas. What was known in Jeans' time? This was the early 20th century, around 1922, 1923. Back then, optical telescopes could only observe hot gas clouds, like the glowing Orion Nebula. But those hot clouds had temperatures of approximately 10,000 Kelvin and very low densities. Applying Jeans' formulas gave absurdly high critical masses, hundreds of millions of solar masses, like entire galaxies. Yet no such giant stars existed. Clearly something was off. Later, in the 1950s, radio astronomy revealed a cooler component of the interstellar medium. Here, gas temperatures were around 100 Kelvin, and densities were higher. Plugging these into Jean's formulas gave 20 solar masses, much more reasonable. Still too big for most observed stars, but closer. Then came ultraviolet telescopes in space, showing us an extremely hot interstellar medium with temperatures of 1,000,000 Kelvin, but also extremely rarefied with huge masses equivalent to entire galaxies. Again, it didn't match what we saw. It wasn't until 75 years after Jean's, long after he and his peers had died, that astronomers, myself included, finally found the coldest component of interstellar gas, the molecular component. This gas has crazy low temperatures, 10 Kelvin or 263 degrees Celsius, a true cosmic deep freeze. But its density is high by cosmic standards, 1,000 particles per cubic centimeter. Plug that into Jean's formula, and you get 4 solar masses. That's a star. Sirius, Vega, 5 solar masses, 2 solar masses. These were finally explained. It turned out the cold molecular component, invisible to optical telescopes but revealed by other instruments, was the true birthplace, the maternity ward of stars. These molecular clouds are enormous. Our galaxy contains roughly 5,000 giant molecular clouds. Each one averages about 1,000,000 solar masses, true monsters of the cosmos. These are the places where stars are born. Now, at last, we understand how it happens. Birth of stars. A cold, big cloud. As it gradually cools, the pressure in it drops. As it does so, it's compressed by the environment, by the pressure of the surrounding gas and by its own gravity. It thickens and cools more and more. But there's no such thing as complete homogeneity in nature. Some part of this cloud is colder and denser than the other, and separate dense areas stand out in it. The rate at which they shrink surpasses that of the surrounding matter due to their higher density, resulting in stronger gravity. As each fragment within the colossal cloud experiences rapid shrinkage under the influence of gravity, the gas within it gradually heats up during compression. Consequently, it tries to cool itself by emitting infrared light from its core. However, as it becomes increasingly opaque, the emission of infrared light becomes hindered, disrupting the cooling process and causing the fragment to heat up instead. The compression persists, causing the temperature within to rise. Soon enough, it reached temperatures of 3 or 4 million degrees. That's the beginning of thermonuclear reactions. What we have in a hydrogen bomb happens in an instant. There it starts and continues for billions of years. Because the density is high, the temperature is millions of degrees, and thermonuclear reactions are going on. I'll tell you later which ones. Meanwhile, the surrounding outer part of the cloud is still cool, still rarefied, but it continues to fall toward the center under the action of gravity. So the very central region turns into a star, and the remnants of matter, so to speak, the construction debris left over from the formation of the star, it also has to go somewhere. And as we can see now, not just imagine, but see, most of this matter goes into orbit around our newly formed star. It has a natural tendency to be drawn toward one another, resulting in them entering into orbital paths. The gravitational attraction between these entities compels young gas clouds to merge together and progressively acquire rotational momentum. The continual act of orbiting serves as the driving force behind any potential collisions that may occur among these celestial bodies. Has anyone ever collided with another vehicle on the road? You get bumped, you get spun around randomly. It's the same for them. But they speed up the process. Remember figure skaters? She starts spinning slowly at first, but then she pulls her arms in. The moment of inertia decreases, and the angular velocity increases. The conservation of momentum causes the same phenomenon here. Initially, the peripheral matter compresses and slowly starts to spin. As time goes on, it winds up more and more, eventually coming into orbit around the central, already young star. This matter becomes part of the cloud and gives birth to a gas disk around the star. It is within this disk that planets eventually form, a process no less mysterious than the birth of stars themselves, and still less clear to us than the birth of stars themselves. But that's for another time. Observing star formation. How did we manage to see everything? Fairly recently, hence the long-running debate, through the creation of a completely new kind of instrument. These instruments are called millimeter and submillimeter telescopes. Since we are discussing the observation of molecules, we need to be able to detect their radiation. And for this purpose, we use shortwave, specifically very shortwave, millimeter wave wavelengths. Electronics only mastered the art of generating and receiving signals with the advent of satellite television. Various frequency bands, from shortwave to satellite, FM, and even shorter radio and television bands, came into existence. Eventually, radio astronomers captured these signals using antennas and receivers, leading to the creation of numerous instruments. Among these, the most essential is a system of radio telescopes situated in Chile, located in the northern part of the Andes on the peak of Chajnantor, a plateau that stands 5 kilometers high. This system is named ALMA, Atacama Large Millimeter Array, or Atacama Large Millimeter Submillimeter Array. It's a magnificent instrument. This is what it looks like in the nighttime moonlight. 60-plus antennas working in unison, looking at the same place in space and accumulating light. Not light, but radio waves. Well, it's hard to even say. It's something between light and radio waves. Very short wavelength, such a peculiar range. But it's exactly the kind of thing you see molecules in, interstellar light. And it showed us something that we'd only ever imagined before, but now we can see for ourselves a newborn star and the gas protoplanetary disk around it. Even these gaps, perhaps, indicate that planets have already formed here and cleaned these corridors, cleaned them from dust, from molecules of gas which shine now in this range. They've sorted themselves and have already cleared the corridors along their orbits. Before this instrument came along, it is a very expensive instrument. It was built with the collective money of most developed countries. We did not participate in it. Well, there's not much funny here, of course, but rather sad. It is a very expensive thing and very difficult to maintain. At an altitude of 5 kilometers, regular scientists are not able to work actively. It is serviced mainly by locals from Chile, from high mountain villages, who have been used to the thin air since childhood, while scientists work 1 kilometer lower at the level of 4 kilometers and conduct observations like this. Formation of planets. In theory, we can consider this process efficient. Nowadays, it can be simulated on computers. As the star shrinks, its center heats up, triggering a thermonuclear reaction. This leads to the formation of a cold protoplanetary disk around it. Although the disk continuously falls into the star, the overall process remains intact, but the radiation from the star itself prevents it from getting too close. It heats up the gas and tries to push it away. The hot gas wants to expand. But where does it want to push off to? Expand where? To the disk region, the equatorial region of the disk. It's dense here. You can't get through it. It's cold. It holds. And along the axis of rotation of the disk, it's almost empty space. Very often, a young star forms 2 such fountains, one upwards and the other downwards. It has 2 tops, and it ejects the excess of this protoplanetary matter in the form of such diametrically opposed streams, jets. If there's anything left over that's not ejected, it eventually coalesces into a small number of planets. Fantasy? Not at all. We are presently observing this process. Directly in front of us lies a frigid molecular cloud. Within it, a star has formed right around this location. Although we are able to detect it using radio waves, it remains unseen through an optical telescope. This star is encompassed by a protoplanetary disk, and it's got hot gas traveling in 2 directions. When it goes away from us, into the interior of the cloud, we can't see it, of course. It's dark. It's opaque. But here, this stream broke through the cloud shell, burst into free space, and we saw it. Here it is, directed towards us, well, a little bit at an angle. We see high-speed movement, around 100 kilometers per second, hitting the rarefied gas. That's where the shock wave forms. Basically, the excess matter is shot out. and we realize that a new star has been born there. Or there's another one, a star right here. One stream is coming towards us, the other stream is going away from us into the interior of the cloud. You can't see the cloud. It's only visible in radio. That's where it disappears from our sight. And this one comes out. You can even see a spiral structure in it, like an auger for engineers. It's what we use in a meat grinder to feed the meat to the knife. It's an Archimedes screw. Apparently, it looks like that for a reason, because there are also magnetic fields that play some role in accelerating this gas. They are so wrapped up in such a screw, and with their rotation, they help the gas to fly out, most likely. But this is already a theory. Although the appearance of this object corresponds to this theory of magnetic acceleration of gas. It's very beautiful. Thanks again to the Hubble telescope for helping with this research. Star formation. There are various regions close to us where numerous stars are currently forming. Interestingly, we have discovered that they prefer not to come into existence individually. We can observe a couple of small clouds where it appears that only a single star has formed. However, as a general rule, they are born together, side by side. Although it may not be simultaneously, it happens at least once, over a short period of time, within a span of 10 to 20 million years. Some of this phenomenon can be seen in the Orion Nebula. Here, we have an image captured using both optical and infrared photography. In the optical view, we can observe 4 extremely hot and bright stars known as the Orion trapezoid. These massive stars were born approximately 500,000 years ago and emit such intense light that they are visible through optical lenses. However, the rest of the objects would be invisible in the optics, but in the infrared, they shine through, and we can see them as newly formed clouds there in the interior. And this is where the star is not quite born yet. It's already formed. It's already become a heat source, but it's still shrinking. This is what's called a Kleiman-Low object. It's only visible in the infrared. Look at how it's actively spewing out the remnants, so to speak, of the gas that hasn't been incorporated into the structure of the star. They just accelerate to tremendous speed and fly like projectiles, penetrating the cloud, flying out into the rarefied interstellar gas. This shows that the young stars are trying to clear their construction site of excess matter, heating up the surrounding space, expanding the cloud, and, in effect, destroying the maternity ward. The formation of their own interior was realized only after a considerable amount of time had passed. Look, here's another example. A massive star. Massive stars are the most active, the hottest stars, has blown a bubble like this around itself. It's blown all the surrounding gas, it's emptied the space of gas. And it's basically empty space around it. It keeps pushing its native cloud, which was once the beginning of this process. It's pushing it around and destroying it with its energy. There are some very massive stars. There's one in the constellation Carinae, Eta Carinae. It's so turbulent, it's hard to imagine where it got all that energy from. In the 19th century, it showed us. It was at one time the brightest star in the sky. Now the matter it threw out has cooled down a bit. The star itself is no longer visible, but we see how actively it, apparently the remnants of 19th century outbreak, is scattering everything around it. There are hundreds of such birthing centers in our galaxy, but they're hard to study. We're sitting here. Our solar system resides within the galactic disk, which is saturated with dust and gas, making it opaque to our view. Consequently, observing the entire expanse of the galaxy is impossible, as we ourselves are immersed in this dense matter. Luckily, neighboring galaxies, akin to maternity houses, provide a more convenient and comprehensive field of study. These galaxies are observable as unfolded images, akin to pictures, on a plane before us. Notably, we have spotted the vast gas cloud, known as the Tarantula Nebula, within one such neighboring galaxy, the Large Magellanic Cloud. Traditionally, the Magellan Expedition, Southern Hemisphere, first sailors discovered it in the sky. Now we call it the Magellanic Cloud. It's a neighboring small galaxy, but it's the largest known hotbed of new star formation. And right here, by the way, right here, we see the most massive star ever discovered by astronomers in nature. It doesn't belong to our galaxy. It belongs to a neighboring galaxy, but its mass is more than 200 masses of our Sun. To be honest, physics can't yet explain how such stars can sustain themselves and not collapse under the influence of their own energy released in them. Well, we'll explain it somehow. The important thing is that we found it. Evaporation of star clusters. What happens next? The newborn stars accelerate the gas around them. In the early stages of a developing stellar cluster, the gas surrounding them exerts pressure, causing the nearby cloud to compact and expel its contents into space. Eventually, the most massive stars in the group will reach the end of their lives and explode. However, our Sun follows a different path and will not experience such an explosion. Over the course of a few billion years, it will gradually shed some of its mass, forming a planetary nebula without any dramatic eruption. Consider, for instance, a star that is 10 to 15 times more massive than the Sun. It will progress through its aging process extremely quickly, taking just 2 or 3 million years, which is extremely fast. At the end of its life, it will release almost all of its matter into space in a sudden outburst. Although these events are rare, we do observe them. Around 1,000 years ago, in the year 1054, people on Earth witnessed the emergence of a new, brilliantly shining star in the Taurus constellation. Now we understand that it was a massive star that had exploded. Over the course of 1,000 years, the material it ejected formed an expanding nebula, expanding rapidly, containing approximately 12 times the mass of our own Sun. Therefore, it was a singular event of matter release, a substance that has enormous energy. The gas is now traveling at somewhere around 2,000 kilometers per second. The kinetic energy is insanely large, and it will push around itself the rarefied, almost invisible environment, actively destroying the cloud for a long time. So, the young stars explode, they heat up around them, and you can see the cloud gradually moving away. This place is cleared. What's left in place of the huge gas cloud is a bunch of newborn stars. What is their fate? By the way, as now established, our Sun, like other stars, was born within a collective of newborn stars. It never existed in isolation and spent its early years in the company of other celestial entities. This fact is now firmly established. We can see that the stars are still in place. This is the Orion Nebula, shown in a very original shot. You can hardly see the stars, but you can see the gas. You can see that the cloud is already such a Barnard loop and has completely left the star formation region. There's absolutely nothing there. Well, we see a gaseous medium, but this is the gas that is now flying towards us from the picture plane. And this gas that is flying perpendicularly there seems denser because we are looking along the walls of this bubble. There it lies, a youthful cluster of stars. What shall become of it? Almost immediately, it became stripped of extra gas, retaining only 10% of the mass which it originally held within the cloud. The cloud was huge, massive. A few percent of its matter turned into stars, and with their energy, the cloud was destroyed. 90% of the mass was gone, and with it went the gravity of that cloud. The stars were moving around chaotically. Suddenly, they found themselves devoid of any binding force. Typically, the collective's internal gravity proves insufficient to maintain unity of this young collective. Here they are on their own, this young star cluster. They've thrown a mass of gas out, and they found themselves, most of them, moving too fast to stay in this place. Even the entities themselves have started to distance from where they were formed. We refer to this process as evaporation, because it closely resembles the evaporation of a liquid. Consider pouring a glass of water onto a windowsill. Return a week later to discover only half the glass remains, and return another 2 weeks later to find the glass completely dry. Where do the particles vanish? Individually, they obtain sufficient velocity to escape and scatter within the confines of the room, never to return to the glass. The same behavior applies to stars. They interact and influence each other through their gravitational forces. The distribution of their velocities follows a specific pattern known as the Maxwell velocity distribution. Consequently, those that possess great speed can break free from this collective at the second cosmic speed. Now, as we observe computer simulations, we can witness how stars gradually migrate away from the region where they were formed. Among these stars, some move slower due to random factors and ultimately fall towards the center of this group. Moreover, there are instances where certain stars depart from the site of formation, while others with slower velocities gather to form a core where these slower-moving celestial bodies concentrate. It is worth noting that the majority of young stars eventually venture away from the region where they were born, while the smaller ones congregate to create compact clusters under the influence of gravity. It is fascinating how you have already formed a cluster, isn't it? But about 2/3 of the stars that were originally in this region have already gone beyond the frame boundaries and were lost there. They just started traveling around the galaxy on their own. So they're gone. Oh well. Our sun also once left the collective in which it was born. But those that moved slowly sometimes form quite large star clusters. The smaller ones were destroyed faster, but the larger ones live for billions of years. We see about 100 of them. We call them globular star clusters, and they have not lost their members since the youth of the galaxy. Well, not all members have left this collective and continue to live there together, moving chaotically. It's a very interesting object. My whole scientific career has been devoted to studying them, because they are ancient. They remember in their structure what was. And here's another globular cluster. It seems that they are right there shoulder to shoulder, yes, stars, that they collided and stuck together. But this is the effect of our atmosphere. It blurs the image of each star. They seem to us such a teddy, so in fact they almost never collide there and fly without collisions. Well, rarely, sometimes they collide, of course, but very rarely. And so, like bees in a swarm, they travel without colliding with each other. Formation of binary stars. Surprisingly, stars often exist in companionship, favoring a family dynamic by residing in pairs or sometimes even groups of 3, observing both double and triple celestial bodies. No commentary. But in the world of stars, it is a regular typical situation, because we have already found out that 2/3 of all stars observed by us are double stars, and about 1/4 of them are triple systems, and a small fraction of them are quadruple and even more complex. Our sun is an exception. The sun is a single star. Astronomers have always been concerned with explaining how double and triple star systems can form. Generally speaking, they can get reunions. This is the result of a computer experiment. We took 3 luminaries, 3-point masses. I've drawn them here as balls and threw them into one region of space. They get closer, they don't collide, but they get so close that they actively attract each other. And look what happens. 3 random luminaries coming together in this area here. They interacted gravitationally so much that 2 of them, the first and the second, merged and lived together as a double star. And where did the energy of their connection go? The third star here received a push at the expense of them, at the expense of attraction to this one, and left this area with great speed, carrying away the excess energy. And so, out of the 3 stars, there's 1 single star and 2 double stars. Can that happen? It can. But you realize that for 2 stars to collide or come close together, there's still some possibility. But for a third star to accidentally fly into the same place at the same moment, the probability is so small that it could happen, but it's very rare. And it, as calculations show, is not able to explain the birth of all double stars. So what can we do? First, we have to take into account the more subtle effects of gravity. Well, for example, if we envision the stars as inflexible and non-deformable entities, such as billiard balls, then when 2 celestial bodies come close to each other, the force of gravity causes them to turn their trajectory, and with the same velocity go to infinity. Nothing happens. They did not connect. But we remember that the stars, despite their apparent solidity, are actually quite malleable. They are influenced by the forces of gravity and can deform due to mutual attraction. Similar to how the moon's gravitational pull affects Earth's oceans and creates tides, stars also induce tidal deformation in each other, causing their shapes to change. Through precise calculations, it is revealed that when a soft star approaches a larger, more solid one, it experiences significant stretching as it is drawn towards it. This stretching energy is a result of their gravitational attraction and is acquired from the star's motion. Instead of a trajectory that propels the star infinitely away, it ends up in an elliptical orbit due to this energy transfer and deformation. It comes back here again, deforms again. The orbit narrows and narrows, 2 or 3 revolutions, and it comes out. The star eventually settles into a circular orbit around the first star, and as a result, they become permanently interconnected in a binary system. This process holds a higher likelihood since 2 entities can encounter one another and allow for a third to ascend as well. But we're looking at a much more complex system. Here we see the famous star Castor. This is the brightest star in the constellation Gemini. Theory of star formation. Look what an interesting structure it has. 2 luminaries next to each other, 2 luminaries next to each other. This group and this group form a double relative to each other. And relative to them, another double system orbits in a wider orbit around them. Whereas 6 luminaries bound together in a single system. A chance encounter has been ruled out. Tides couldn't help either. How did nature realize such an object? And the idea came up from the other side. Mathematicians have long studied the deformations of bodies that have gravity and rotate and slowly shrink as they cool down. Researchers have explored abstract problems related to the compression of shapes within an ideal fluid. Although this abstraction separates from reality, it allows us to investigate the compression of a uniformly dense body at its initial stages. With time, as the body shrinks, its density increases. This change leads to the body gaining momentum due to its reduced size. The momentum causes the rotating body to flatten, ultimately transforming into a spheroid shape. The flattened body resembles a globe, with its flattening occurring along the axis of rotation. This transformation continues as the process progresses. Then the deformation gradually increases, stretching across the equator. And at some point, if nothing happens, it expands in compression, spins more strongly, and turns into a pancake of such a kind, a disk rapidly rotating, which still remains a single body. But at some point it has the option to go down a different evolutionary line. If suddenly the central part of this substance bounced to the periphery, then instead of a pancake, we get a ring. A ring is also a single body. It's a long way from a double star. Alright, let's see what's next. And it turns out that we had one more possibility of bifurcation, the separation of evolutionary curves into 2 directions. But an elongated, as my students say, cucumberoid. And it could rotate around a short axis and extend in 2 directions, offering a slight perspective. The cucumber exhibits another characteristic where it can stretch out and transform into a pencil while rotating. However, we are not interested in this specific aspect. Nevertheless, we notice another point of division. If some external force disturbs this shape slightly, the substance can disperse to the ends of the ellipsoid, elongating and creating 2 bulbils. At this juncture, we begin to perceive a hint of 2 separate objects within the dumbbell-shaped body, which gained recognition through the French mathematician Poincaré's description. As the connecting part becomes progressively thin, the matter will migrate towards the dumbbell's ends. Ultimately, it will split into 2 distinct objects. It is possible for the object to break into 2 separate fragments. The calculations indicate this possibility and suggest that such an event could lead to the formation of 2 distinct objects in the future, potentially even 2 separate stars. Disintegration and fragmentation of stars. A 3-dimensional hydrodynamic calculation confirms this. What's more, it shows that it's not just binary but more complex, This, then, is a calculation made approximately 15 years ago or so. Alan Boss described the phenomenon I'm about to explain. Over time, this concept has become more refined and detailed. We observe that the cloud has been gradually shrinking, and our focus lies within its central region. As the cloud shrinks, we reach a point where two fragments separate from each other. These fragments then split in half, resulting in the formation of a unique quadruple star system as promised by nature. As to where this matter will eventually go, the calculations were unable to provide a clear answer due to the excessive amount of computer time required. However, the primary substance divides into four distinct bulbils, giving rise to a system of two double structures. Both of these structures orbit a shared center of mass. Through the process of cloud compression, nature achieves this remarkable phenomenon known as fragmentation, gravitational instability, and subsequent disintegration in separate structures. We do observe such objects in space. This is such an emulation in Triad, an artist's picture, but in reality we observe such stars, which are almost stars and have not yet lost their mutual connection. The isthmus between them is preserved. It is unknown. Most likely they will break up and become two separate luminaries, but we see such objects. Of course, not as beautiful as in this picture of the artist, but by their properties, by the change in brightness of the mutual, we realize that this is the shape they have. Here is a standard model of the sun, and we see how the temperature from tens of millions, there from 15 million degrees in the center, gradually falls to the surface of the star and almost to zero. There are a few thousand degrees on the surface. Energy sources for stars. The pressure within a star decreases as the energy generation increases, causing the center of the star to be hotter due to thermonuclear reactions. As a result, the matter at the center of the star does not produce energy, but instead transfers it to the surface before being released into space. This widely accepted model of internal parameter distribution in stars has left astronomers with no doubts. However, the question remains, what keeps the star warm and maintains its internal temperature for billions of years while allowing it to continuously lose such a substantial amount of energy without undergoing any noticeable changes? It was not immediately clear what the source of this sustaining energy could be. In principle, what sources can be considered to explain this phenomenon? In the early 19th century, the concept of chemical reactions remained largely unknown. People generally believed that ordinary chemical reactions were responsible for the energy generated in stars. It was believed that matter inside a star, such as carbonaceous substances like coal, oil, or gas, would bind with oxygen, similar to how carbon dioxide is formed when fuel burns in a stove. This process would release energy. Scientists attempted to calculate how long the sun could shine, solely based on chemical reactions as its energy source. For instance, we could measure the amount of energy released per kilogram of burned fuel to estimate the duration of a star's functioning. We possess knowledge about the sun's mass, speed, and radiation power, which is unbelievably enormous, close to 10 circumflex 27 watts. By dividing this power by the energy released during a chemical reaction, we could determine the sun's potential lifespan. Unfortunately, it turns out that even with chemical reactions alone, the sun could only sustain its current level of brightness for several thousand years. A perfect match with the biblical idea of the age of our world. The early 19th century scientists were thoroughly impressed by its greatness, to the point that even the smallest coincidences made them joyful and confirmed the validity of the theory. However, as the mid-19th century rolled around, geologists began to question the idea of the Earth and the entire solar system being such a young age. They started calculating how rapidly sedimentary layers built up at the bottoms of lakes and seas, leading them to estimate that it would take hundreds of thousands, if not more, years for this to occur. This forced physicists to consider alternative ways to explain the continued existence of the sun. They discarded chemical reactions as a viable source of energy and turned to gravity. The idea was that when a stone falls from above, and makes impact, it generates heat as the potential energy of the gravitational field converts into thermal energy. Additionally, a weight can be lifted on a pendulum clock, which then takes 24 hours to fall, generating energy throughout this process. The clock weight descends and releases its potential energy. The mass of the clock weight on the acceleration of free fall. On the height of the lift, it descends. The energy is released, passes in the end into heat, in the gears, in the clock. A good source of energy is the sun, a massive body, a large supply. We did the math. What could fall on the sun? We looked around. And in the solar system, there's a lot of dust in the space between the planets. There's so much of it that sometimes we can just see it. Especially in equatorial countries, after the sun goes below the horizon, we see such a faintly luminous but quite noticeable cone against the black sky. We call it the zodiacal light. It's along the ecliptic, along the zodiacal constellations. And we realize that these are dust particles that reflect the light of the sun. The sun's light is scattered on them. And we're a field disk that's in the space between the planets. Yeah, so dust is falling. Dust, meteorites. Small bodies fall on the sun and warm it with their impact. Something seems to be missing here. The calculations indicate that there is an insufficient quantity of this substance. Then, a commendable group of physicists, namely Meyer, took the initiative. Gengoltz and Kelvin performed the necessary calculations. They said, "Come on, what's on the outside? The sun itself is falling in on itself." As the sun's matter gravitates towards its own center, its upper layers begin to collapse onto the layers beneath it, causing the release of heat. If the sun continues to shrink and compress in its own gravity, the process of heat release will continue. And the calculation showed, in simple form, that such a source of energy will be enough not for 3,000, but for 30 million years. Once again, it's an interesting thought that scientists have discovered. Geologists have estimated that the Earth is millions, even tens of millions of years old. Meanwhile, astronomers have also substantiated the presence of an energy source that allows the sun to radiate for such extended periods of time. This discovery has put everyone's mind at ease, as it has helped elucidate these phenomena. It's worth mentioning that this theory has captivating implications. In the life cycle of any star, there are moments or entire eras in which gravity bestows its luminosity upon them. The birth of a star brings forth an epoch where it condenses from a nebula into a compact object, subjected to the relentless heat generated only by gravity for tens of millions of years. Similarly, the death of a star entails the core being stripped of other forms of energy, causing it to collapse into a highly dense state, relying on gravity as its primary source of energy. Nonetheless, additional energy sources are still required for the star's core existence during its longest evolutionary stages. Thus, a mere 30 million years falls short. Radioactivity and the nuclear reactions. When radioactivity was discovered, the chemical elements, uranium, plutonium, and so on, were found decaying at the end of the periodic table. At the very end of the 19th, beginning of the 20th century, radioactivity was discovered. It was used to measure the age of the Earth's rocks, and it turned out that the Earth was not millions, but billions of years old. So astronomy was out again. We had to stretch the evolution of the sun by billions of years. But the first idea was that uranium decays. So the sun is made of uranium. Something's decaying inside of it. Well, luckily, they didn't know that a lot of uranium is a good atomic bomb, and the sun would explode in a heartbeat if it had that much uranium in it. No, they needed another idea. And only in the end they paid attention not to the end of the Mendeleev table, not to heavy elements, but to the very beginning, and realized that not only decay, but also synthesis of matter from heavier elements, from hydrogen, from helium to carbon, also provide energy release. These are called thermonuclear reactions, but for quite a long time physicists could not understand how they occur. The thing is, fusion involves bringing chemical, nuclei together. Say a hydrogen-proton nucleus. In order for them to fuse and form a more complex nucleus, They just have to be brought closer together. And these are two protons, two positively electrically charged pieces of matter. They repel as homonymous charged particles. Try to bring them closer together. They repel. So, to bring them closer together, they have to be accelerated to a high speed. This idea is realized when we accelerate them into each other in the particle accelerator. But there's no accelerator in the interior of the star. We make them here in the lab. In the interior of a star, the only process that can accelerate the particles so that they stick together properly, get close to each other, is temperature. The higher the temperature, the more active the motion. We've calculated what temperatures are needed for the fusion reactions of the nuclei of light atoms. Billions and billions of degrees. Those are the temperatures that would occur in a hydrogen bomb explosion. But there are no such temperatures in the interior of the sun. Calculations show that it doesn't exist. We're at an impasse. It seems that the only source of energy in stars is thermonuclear reactions, and the conditions in the interior of the star do not allow them to flow. And that's when a young Leningrad physicist, Georgy Gamow, solved the problem for the first time. He said, "So we need to accelerate the proton so that it overcomes the potential barrier. That is, for it to approach, here is the second nucleus, for it to approach it, to pass over this potential barrier, and having approached so close, approaching the second proton, would be able, due to nuclear forces, which are not electrical but of a different type, to be bound with it forever into the nucleus of a more complex chemical element. Here it needs to accelerate in order to rise to this, as physicists say, potential barrier, to overcome the repulsive force. It can't. It doesn't have enough acceleration due to thermal motion to rise above this potential barrier." And Gamow, with the help of quantum mechanics, which had just been created at that time, showed that any small particle has a probability, without going over the barrier, to pass, as they say, to tunnel, as if to tunnel under the mountain, to pass this distance, only due to the fact that quantum mechanics says that any particle is spared in space, that it exists simultaneously in several places, and it may immediately end up in the next place, no matter what wall separates it, no matter what wall separates the 2 points. It's the tunnel effect, so-called. It was discovered by a young man, less than 30 years old at the time, Georgy Gamow. Then he worked in the US and became a great physicist. By explaining this case, he showed that thermonuclear reactions can occur even at not very high temperatures. 5–10 million degrees. It's not very high, and yet it happens. Two protons flying, coming together, and they get so close that at some point they're going to come together into a stable system. In doing so, one of them undergoes a transformation. It transforms from a proton into a very similar particle, but without an electric charge, a neutron. And it throws its electric charge away in the form of a positron, the antiparticle of the electron. And then, having thrown away the positron and a small addition in the form of a neutrino particle, it forms two protons. This is such a connected system. A proton plus a neutron. The nuclear force between them is in effect, but there's no electrical repulsion because the electrical charge has gone with the positron somewhere out there in the distance. What is this? It's still a nucleus of hydrogen, but now it's a heavy isotope of hydrogen, deuterium. Every now and then, it meets another proton. There are lots of them flying around. And what happens? They combine, now that's easy, into the nucleus of a new chemical element. It says helium. Two electric charges plus a heavy particle with no charge. That's a helium-3 nucleus. They fly around until they meet the same helium-3 nucleus. And what happens to them? They merge, the extra particles throw the two protons out of their composition. They're too strongly repelled by the electric charges, and God forbid, they fly off and form two protons, two neutrons. Physicists call it an alpha particle, but in fact it is a helium nucleus of the standard heavy isotope helium-4, but which we have in balloons. When we hold them on a string, they want to fly away from that very helium. And when they do, the extra protons are ejected with such force that they carry enormous energy and heat up the gas around them. That's the release of energy in thermonuclear reactions. The process of thermonuclear reactions is a highly complex scheme that unravels the inner workings of the sun. It begins with the merging of protons, forming a deuterium nucleus. This crucial step initiates almost all subsequent processes. Another proton is then added to create helium-3, which eventually transforms into helium-4. In this manner, 4 protons combine to form one helium nucleus, while also producing positrons and neutrinos as byproducts. Although there are some minor reactions, they do not significantly contribute to the main effect and are only considered in exact calculations. If the star is slightly more massive and hotter, there is potential for some fascinating thermonuclear reactions to take place. These reactions can be considered catalytic processes in the eyes of a chemist, meaning that the substance involved is not consumed, but rather aids and enhances chemical reactions with other substances. For instance, if a star contains carbon, even in small amounts, it has the ability to bind 4 protons to itself. During the process, a helium nucleus is ejected while the carbon is transformed into nitrogen and then into heavy carbon and oxygen before returning to its original form known as carbon extwuit, the standard carbon. At the same time, hydrogen is being transformed into helium through a reaction called the CNO cycle, which is an abbreviation for carbon-nitrogen-oxygen cycle. Although it occurs less frequently, this cycle is the primary source of energy release for massive stars. The chain reaction continues as neon is produced from the fusion of helium, followed by the addition of carbon to obtain carbon and oxygen through the absorption of helium nuclei. This chain process leads to the expansion of the periodic table due to the occurrence of these thermonuclear reactions. However, with each subsequent step, the process becomes more complex and challenging. Take note of the electric repulsion between 2 protons due to their charge of 6 protons, which requires extremely high temperatures for this reaction to occur. The more massive the star, the hotter it is, and these reactions happen. Here are the stars with their masses in units of the sun's mass, which we know today from 50 to 1% approximately of the mass of our sun. The parameters: the size of the star, the density of the center, the temperature at the center, and the radiation power, the luminosity of the star. These calculations are very accurate, and we have no doubt about the numbers. We checked it all on astronomical observations. So today we have a pretty accurate picture of not only external parameters of stars, total luminosity, total size, total mass, but as you can see, we can guarantee what the temperature in the center is in millions of degrees. That's a colossal temperature right there, almost 40 million degrees in massive stars. The sun is not very large, about 15 million degrees. The low-mass stars have very low temperatures. And this, in general, is a reliable result of astrophysical calculations. But how do you test it directly? How can we see those thermonuclear reactions that are going on deep inside the star? While we only indirectly see some effects of these reactions in the form of general radiation, how can this be tested in practice? Or, neutrinos and their role in the life of stars? Well, we have a clue. Look, when 2 protons merge, one of them turns into a neutron. A positively charged electron is ejected. And what else? This one doesn't have long to live. It immediately meets a negatively charged electron, annihilation, and they both disappear, become quanta of light. That's something we'll never see. It disappears into the depths of the star. And then there's this neutrino particle. The neutrino interacts so weakly with any form of matter that, once born, it almost leaves the sun at the speed of light, penetrates it without noticing the entire thickness of matter, and in a few seconds it leaves the surface of the sun, goes into space. And then 8 minutes later, it reaches the Earth. That is, 8 minutes ago, those neutrinos which have arrived here now were born in the core of the sun. So this presents an exceptional chance to investigate the activities occurring in the center of our celestial body. The only dilemma is determining how to capture and record them accurately. Our laboratory setup, our detector, they'll pass through it without noticing. Suffice it to say that right now, every single square centimeter of our body, including the tip of our nose, is penetrated by a mind-boggling influx of around 1 billion neutrinos emitted by the sun per second. We don't notice it. Billions of neutrinos are passing through our body right now and going further. And it's evening now. Where's the sun? Under the horizon. There on the other side of the Earth. They're passing through the globe, through us, and they go that way. And the device doesn't notice. So the device must be massive to intercept at least something from this stream. The first such device was made by an American physicist, even chemist experimenter Raymond Davis in 67th year. And so from the 68th year, he tried to register solar neutrinos. The instrument was built deep, 1.5 kilometers deep, in a shaft underground, so that this crust of the Earth would screen out everything from space except the neutrinos, which no layer of Earth can trap. He made a big tank, filled it with a substance in which there was a lot of carbon and carbon atoms, the most sensitive to catching neutrinos. They sometimes turn into radioactive argon under the influence of neutrinos. That's what Davis was going to record. The experiment? Well, I don't know. I just don't have the imagination to realize it. Almost 400,000 gallons of stinking liquid. And this is the liquid the dry cleaners use to clean our stains. A very strong-smelling volatile liquid. Tetrachloroethylene, or perchloroethane, as it used to be called. In a gigantic tank, a week's time saw the birth of 12 argon atoms. Some of these atoms needed to be extracted from the vast volume for the purpose of measuring their quantity and determining the number of interacting neutrinos. The scientist bore the responsibility for this task, dedicating not just several years, but even decades to conducting the experiment. Eventually, it was conclusively demonstrated that neutrinos do indeed originate from the sun. It seemed like a victory for astrophysics. It led to a significant burden within the field of astrophysics. In fact, one could even describe it as a crisis. It led to a significant burden within the field of astrophysics. In fact, one could even describe it as a crisis. Personally, I was witness to this development from the 1970s onward, when these findings began to surface through publication, because the neutrino flux measured was 3 times less than the theoretical prediction. It didn't add up. We were expecting the same number, and they came in 3 times less. Physicists told us, "You don't know how the sun works, something else is going on there." We measured the neutrino flux, and we see that there are fewer neutrinos than astrophysics predicts. We timidly told the physicists, "Yes, we will try to clean something up." And we did. We made new models of the sun, where the core has a different chemical composition, that it is spinning, that there is a magnetic field. Somehow we wanted to slow down the reaction so that the theory would give fewer neutrinos from there. "But," the physicist said timidly, "maybe you don't quite understand what a neutrino is. We have a theory of elementary particles, the standard theory." "All right, well, we'll try. We'll figure something out." And we did. We made other detectors. The thing is that neutrinos come in 3 different types. The birth of an electron or positron corresponds to an electron-type neutrino. But there are also brothers of the electron. These are the mu meson and the tau. The mu particle and the tau particles are different types of neutrinos. These are the particles we usually focus on. In typical reactions, only electrons are created, and we anticipated them to come from the sun. We were not expecting any other types of neutrinos. The physicists assured us of this. Neutrinos have no rest mass, so they travel at the speed of light. This means that time effectively stops for them. As a result, when neutrinos travel at the speed of light, they do not have the opportunity to transform into different types of particles. Even though they are generated on the sun and detected on Earth, it is essentially the same moment in time for them. They simply do not have enough time to undergo metamorphosis. Therefore, we were only anticipating the presence of electron neutrinos. Well, gradually, new detectors were made. And here, in the neighborhood of the year 2000 in Canada, was built a new detector of neutrinos, which had the ability to register not only electron, but also muon, and also tau. And when all three types of neutrinos were registered, it turned out that in the sum of their arrives from the sun, as much as the sun should be born electron. And that means that on the way from the sun to the Earth, they experience mutual transformations. Instead of the flow of electron flux, we have the same flux, but of three different colors, three different flavors, as physicists say. Well, it's conditional. They don't have flavors, of course. And then the astrophysicists got into a pose and said, well, we knew how the sun worked, but you were wrong about the neutrino. It has a rest mass. It travels slower than the speed of light, although not by much, almost the same, but a little slower, which means it can transform on its way from the sun to the Earth into other types. And now we look arrogantly at physicists and wait for them to create a new theory of elementary particles, which would take into account these transformations. It's a big victory for astrophysics in this intellectual debate. Well, all right. Energy was born somewhere here, where it's hot and dense and thermonuclear reactions are taking place. And the only way it can leave the stars from the surface into outer space. So how does it get from here to there? Well, we know three types of energy transfer. There's conduction. When you put a hot spoon in your tea, it gets hot on the handle. It's convection, where warm air rises up from a hot body. And it's transfer in the form of radiation. Infrared light. Infrared radiation doesn't travel through the sun, and heat conduction is weak there. But convection, that's a good process. We heat the liquid from below, it boils and carries the heat to the top, and then it goes from the pot to somewhere in the kitchen. We're familiar with this process, and it happens in stars too. And it mixes the matter in the stars quite efficiently and carries the heat from the interior to the outside. It's helped, of course, by conduction in the form of quanta of light that break through the hot plasma. But convection is almost the main carrier of heat from the interior of the star to the outside. The star is boiling, constantly boiling, heated by its core. Classification of stars. So we have already covered the basic elementary processes. Now let's delve into the life of stars. Firstly, stars are incredibly diverse, to varying temperatures on their surfaces. Some stars reach temperatures as high as tens of thousands of degrees, while others are in the thousands. There are even some that are so cold that you could likely heat a piece of iron in your kitchen to 3,000 degrees, and it would emit a similar glow to a star, or at the very least, something close. We see that stars differ not only in their temperatures, but also in their masses, giving rise to various evolutionary sequences. When we observe a star, all we can perceive is its outward appearance. We are able to measure the amount of energy it radiates, the strength of its radiation, and the temperature found on its surface. All this information is right there before our eyes. So let us continue to explore this fascinating world of stars and discover more about their intricate lives. We can construct a two-dimensional picture of the star's radiative power, in units of the sun's radiative power, of course. The sun as a standard is always taken. The surface temperature. And it turns out that most stars in the universe are distributed along this diagonal. Powerful emitters are hot on the surface and weakly powerful, and quite cold on the surface. Well, that's not really surprising, is it? The hotter the surface, the more heat escapes from it. But it turns out that there are stars that are cold on the surface but powerful emitters. What does that mean? It means they have a big surface. So they're big in size, we call them giants. And then there are the opposite stars that are hot. You see, the surface temperature of white dwarfs and red giants can reach tens of thousands of degrees, making them very warm. However, despite their high temperatures, they emit minimal light and heat due to their small surface area. These types of stars, consisting of a small fraction of the total, are known as white dwarfs and red giants. The main sequence, which comprises around 90% of all stars in our galaxy, is commonly represented by the Hertzsprung-Russell diagram. This diagram was first developed in the early 20th century by two astrophysicists, Hertzsprung from Europe and Russell from America. It serves as a temperature and luminosity diagram, highlighting the main sequence and its significance in understanding stellar evolution. While more specific classifications exist within the professional community, such as subgiants and supergiants, these details are not necessary for general astronomy courses. Hence, the main sequence of stars illustrated in the diagram caters to both professionals and enthusiasts. Deciphering the evolutionary analysis reveals how the fundamental attributes of our Sun evolve with time. At present, these attributes are considered as benchmarks, where the Sun is currently 4.5 billion years old, with a surface temperature, size, and radiation output serving as reference points. In the past, the Sun was a little bit smaller in size, had a much smaller radiation output, and about the same surface temperature as it does today. And in the future, we can continue to do these calculations as long as the physics of the processes are clear. As the Sun expands in its lifetime, it will increase the power of its radiation and cool down a little bit on the surface. Not very much, but it will decrease its surface temperature by a factor of 1.5. But by increasing the surface area of light, the radiation power will increase. Fortunately, we're lucky with the Sun. Because if we were to model the life of stars similar to the Sun, but with a slightly different chemical composition, it turns out they would have a very different life. There are stars like this around us, luckily not our Sun. Here's a star with very few heavy chemical elements. Astronomers call as heavy elements everything except hydrogen and helium. These two elements. Well, that's how we got hydrogen and helium, the main components, and we even call everything else metals. Although carbon, oxygen are not metals, everything else is metals. There's a fraction of a percent of them, and our Sun has 2%. Like a pinch of salt and a micro pinch of salt. Is there a big difference between the two? It's a big difference. Because these rare chemical elements act as a filter for the rapid passage of energy from the interior of the Sun to the surface. They intercept the quanta and make them move more slowly to the Sun's surface and stretch its life out over a longer period of time. The Sun is still here today, 4.5 billion years old, and it has another 4 or 5 billion years of quiet evolution ahead of it. Then there's a dramatic change. And if our Sun had been born with less heavy elements, it would be ending its life today, maybe even yesterday. Evolution of the Sun. And man would not have had time to become man. So at the level of monkeys, our solar system evolution would have ended, and you and I would not have had enough time to evolve into Homo sapiens. But fortunately, the Sun is slowly changing, and it has a few billion more years of quiet life in store. And then there will be violent change. Here's the evolutionary model of the Sun again. In the center, the density builds up and reaches a very high value. Why? Because hydrogen is burned, helium is produced there instead, and it does not participate in thermonuclear reactions at those low temperatures, which are really in the Sun's interior. And it, as a slag, is deposited there, compacted in the core of the Sun. It becomes small, gravity on its surface is strong, and hydrogen there is heated to a high temperature and burns more and more intensively. But it burns up there. See, in the core of the Sun, helium is accumulating and the amount of hydrogen is decreasing. And there is almost one inert helium core left in the core, incapable of thermonuclear combustion. It's compacted, and there's still hydrogen around it. And it continues to participate in thermonuclear reactions and becomes more and more intense, released as a heat source. And in the Hertzsprung-Russell diagram, the Sun during its, so to speak, final stage of evolution will begin to increase its luminosity rapidly, and its size will increase 5 times, 20 times, 50 times. It starts to expand. Why? Well, I've come up with this analogy with a balloon. Look, we buy a balloon, but we used to buy them not inflated, but always in the form of this rubber band. It's opaque. We start to inflate it, and as it expands, it becomes more and more transparent. The same substance spreads out over a larger surface and becomes thinner and more transparent. When, in the interior of the star, Heat is released more and more actively. The star has to dump the heat somehow, or it's just going to explode. Just explode. It expands, and as it expands, it becomes more and more transparent, and it's easier for radiation to escape. That's the reason why stars expand at the end of their life. The radiation power builds up, and the shell expands to release the excess of that radiation. This is the entire timeline of the sun's series of evolutionary changes from its birth from a cloud of gas, as it evolved, burning hydrogen in its interior. Today, we're about halfway there. There will be an increase in the power of its radiation going forward, but so far it's not changing much yet. There's about 10% increase in the sun's radiative power over 1 billion years in our era. That's almost imperceptible. 1 billion years is only 10%. But then it starts to change very rapidly, and in about 100 million years, the sun will swell into a huge red ball. We call it a red giant, a really big one. It will lose its shell, it's already inflating. It will simply leave the core. It will expand, and the core will remain, and it will cool. The helium core, incapable of further thermonuclear reactions. In other stars, helium can continue the fusion process at high temperatures, and the sun is such that it will almost leave its helium intact. It's not a fantasy. We observe solar-type stars at different stages of evolution, and we see that there are giants, and as they age, they become more and more gigantic. The sun is like this today, and it will expand to a giant size. So let's compare in this illustration what the sun is like today and what it will be like in a few billion years. And how does that end for the planet? Well, of course, I'm showing you a robust version of evolution. When we do accurate calculations, we know how each star, depending on its initial mass, will travel along this Hertzsprung diagram. And we also know this. There are some stars that are not yet stars, those that are never destined to become a real star in their lifetime. Notice, this is our sun. This is one mass of the sun. These are the more and more massive stars. These are the less massive ones. But here's 10% of the sun's mass is where this picture ends. Why? Because if a star has an initial mass that's less than 10% of the solar mass, or 8% of the solar mass, it will never be able to start the fusion stage in its interior. The temperature there won't rise above 3 million degrees. Not even hydrogen can burn. Will not be able to participate in thermonuclear fusion. And it will, in its attempt to become a star, start to cool and cool and cool and forget that it ever wanted to be a star. And a slightly more massive body will start a thermonuclear reaction in its interior and will remain in a stable state for billions of years, gradually burning hydrogen, turning it into helium. Here's a small difference in the initial mass, makes a big difference in the future body. These are the kind of non-stars we call brown dwarfs. They wanted to become a star. They wanted to light up and then for billions of years, but they didn't have enough mass and they are more likely to become planets, gradually cooling down than real stars. So that's how we imagine the life of the sun today. The cloud of gas shrank, heated up, and having reached this point on the Hertzsprung-Russell diagram, it ignited a thermonuclear reactor in its interior and burned hydrogen for billions of years. When it burned it, it quickly began to expand, became red elegance, dropped the shell, and the core cooled down and turned into such a slag. First a white dwarf, then a cooling, very small compact object. During this fading already in the last stages of evolution of the life of the star, for a while, it becomes very restless. Its stationary state is no longer possible. At a specific area on the diagram, the star begins to pulsate. The change in behavior occurs as it crosses this particular region. We've always seen stars like this, but it took physicists a long time to understand it. Here in front of you is a series of photographs of a star cluster. This is the center. This is the periphery. See how some of the stars are flashing there? We've been tracking this for a long time. We called them variable brightness stars, but we couldn't understand the process. We felt like they were pulsing, but for what reason, I don't know. Their cause was first discovered not by an astronomer by profession, but by a radiophysicist, Sergei Zhivakin. He was working in Nizhny Novgorod, Russia. He was a specialist in oscillatory processes, and in radio engineering it is studied all the time. And he, interested in astronomy, in particular in variable stars, for the first time realized the physics of this process, that there is a valve mechanism that works there. It lets the radiation through, then holds it near the surface of the star, and the star changes its brightness on a regular basis. As the heart beats, as it shows itself on the cardiogram of hearts, so the star at a certain stage of evolution begins to pulsate. Well, you'd think we'd figured it out and forgotten, but it turns out that it's these pulsating stars. They're called Cepheids. After the first one discovered, Delta in the constellation Cepheus, they've been extremely useful and they've helped us make a number of discoveries. Why? Because the period of their pulsation turned out to be related to their radiative power. This was first discovered by Henrietta Leavitt, an American astronomer, a deaf-mute woman, by the way. She was very active in the early 20th century, and she saw in her statistical observations that the brighter a star shines, the longer the pulsation period of its surface and brightness fluctuations. So when we see such a pulsating star in some distant galaxy, we can easily, in a few months of observation, find out what period it's pulsating with and find out the exact value of its radiation. Of its own radiation, the power of its radiation. And by comparing it with the apparent brightness of the star, we can tell how far away it is from us. It's a very hard problem for astronomy to measure the distance to distant objects, and here the Cepheid stars have proven to be the most reliable indicators of the distance to distant galaxies. So important, in fact, that they're the ones that allowed us to discover the dark energy in the universe because they make it possible to measure the distance to galaxies. So the expansion rate of the universe is related to the distance to galaxies. It's a colossal discovery, essentially made by one lady. It's a remarkable story. She was housekeeper to the famous astronomer Pickering. And he managed a small group of men, as only men were involved in scientific work at the start of the century. However, when she noticed his work, she became intrigued, and he shared his knowledge with her. She started assisting him at home, not only in cleaning, but also in performing calculations. He realized that she was more efficient than the men on his team, so he decided to disband it and instead hired 24 women for the same budget he had for 6 men. This team came to be known as Pickering's Harem, and together they achieved great accomplishments. No, only scientifically. And they made discoveries that we still use today, Henrietta Leavitt, and this dependence, other spectral characteristics of stars to measure. They worked magnificently, and to this day we still have half of the staff in our institute are women. That's what is atypical, generally speaking, for science, especially in the 19th century. In astronomy, women first showed themselves so actively. So we're coming to the final stages of a star's life. Where do they end up? We've already figured it out. Those that are similar to our sun, having turned into red giants, inflated, gradually lose their shell, it continues to inflate and turns into such a cloud of gas leaving the star. This is how we imagined all planetary nebulae, because the star is a ball and must lose gas from its surface very symmetrically in the form of a ball expanding in all directions. Yes, the Hubble telescope has shown us there are such stars, but it has shown us that there are also such planetary nebulae, which surround themselves with some incredible pattern of lost gas, and there are more like this. We have already seen these planetary nebulae, and there are more like this. So to understand how a balloon star can organize around itself such a complex pattern of material, of matter moving away from the surface, we're not yet able to understand. There is a set of separate shells, and an incredible picture inside, and 2 jets that are ejected in diametric directions. How the star manages all this, by what forces it does this, gravity plus magnetic fields, plus something else obscure, is beautiful and has yet to find an explanation. Well, in the end, okay, it sheds half of its mass, and the other half remains as the dying core of this star. Planetary nebulae are well studied. The nucleus heats up the surrounding gas. It glows, we will see, and the nucleus itself is a small object. What's left of the star, it's often comparable in size to our planet, sometimes smaller than even white dwarfs. They were discovered rather late. They're faintly luminous. You can hardly see them. They were discovered in the middle of 19th century. And here was a young theorist, Indian. At that time, he was educated in India, worked for the first years there, Subramanian Chandrasekhar. He was young, I think 24 years old, a recent graduate of the University of Madras for the first time made a calculation. And what is the fate of the white dwarf? And it turned out that the white dwarf cannot be very massive, that it maintains itself in equilibrium. Gravity is compressing it, maintains itself in equilibrium by quantum mechanical forces. There is degenerate gas in it, and for a long time cannot resist gravity. And according to Chandrasekhar's calculations, it turned out that if we cold body, and the white dwarf is in fact cold, like a planet, build up its mass, then at first this planet-like body will be a body, then the type of white dwarf. But when it reaches a mass of about 1.5 solar masses, no white dwarf can keep itself in equilibrium and will have to shrink even more, formally to 0 in size. He was censured for this. He was reviled. They didn't believe in his results. They scolded him. He first wanted to work in England, but they almost shamefully expelled him from there, saying that such a thing could not happen in nature. He went to the US and became a Nobel Prize winner in physics because his calculations were confirmed. And we now know that white dwarfs cannot be very massive, but can be no more than 1.5 times more massive than our sun. And we actually observe them. It's especially interesting when they're paired with another star. Here's one of the most well-studied stars, Omicron, the constellation of Cetus. And this is what we see in the telescope. This is what we see in another telescope, into X-rays. And it's up to the artist to interpret what this system actually looks like. A normal, ordinary star, like the sun, and next to it a white dwarf, and they revolve around a common center of mass. And the white dwarf, although small but massive, and it pulls the matter from its neighbor, and it gradually falls there, rotating for some time in the disk because the orbital motion is preserved. And so such double systems, where a small but massive white dwarf pulls the matter from its neighbor, we observe quite a lot today. And so these white dwarfs, referred to as they, become visible to us because they are small and unnoticeable. However, when they attract matter from their neighboring stars, an accretion disk forms and emits bright light due to the heat generated by the friction of its rapidly rotating layers. This gas emits various forms of radiation, including infrared, ultraviolet, and even X-rays. The capture of extra matter continues until a significant amount of pure hydrogen gas accumulates on the white dwarf. This accumulation process is a continuous cycle of matter falling onto the white dwarf that's already capable of a thermonuclear reaction. There was a white dwarf made of helium, which at this temperature does not catch fire, and it steals from its neighbor almost pure hydrogen. And hydrogen is just waiting to start turning into something new. And when it has accumulated there a lot, it actively begins on the surface of the white dwarf synthesis of hydrogen, helium synthesis from itself. And this, in the form of an explosion, occurs. You get a flash, and in the 16th, 17th centuries and up to now, we observe from time to time flashes of bright stars in the sky. And now we understand what it is. In 1901 year, we saw a flash in the sky, and today we take pictures. We see there is a double system, a white dwarf and a normal star next to it. And during thermonuclear explosion on the surface of the white dwarf, the ejected matter has already dispersed today. And it still continues to accumulate, gradually building up a critical mass of matter over the span of a few decades. Once again, in a few tens of years, it may ignite this fresh matter and unleash a powerful thermonuclear explosion upon its surface. However, that is not the only intriguing destiny that awaits. Consider the two white dwarfs that emerge from ordinary stars within a binary system. These could be either. As they orbit around a common center of mass, they gradually converge. The reason for this is that this dual mass system, are emitting gravitational waves. Now we register them on Earth, we know that this is a normal physical process. Through the loss of energy to gravitational radiation, the two bodies move closer together and finally merge, collide, and unite. They form a massive conglomerate that gradually loses equilibrium. Eventually, this conglomerate undergoes a rapid shrinking process, leading to intense heating and eventually a thermonuclear explosion. As a result, the entire system is obliterated entirely. And that's what we observe. That's what we call supernova star explosions. So the way we envision the life of a star today is this. A small star, like the Sun, at the end of its life loses matter in the form of a planetary nebula, turns into a white dwarf. But it can, if there are more white dwarfs near it, stick together with it and explode like a supernova. Either it will completely explode, nothing will remain of it, or a piece of it will shrink into a neutron star, an even denser and quite massive body. And then, the cores of stars that surpass the Sun in mass are typically already contained within the star. The nucleus is so massive that it transitions to the white dwarf phase and promptly transforms into a neutron star while inside the star. This process results in a substantial release of energy, causing the star to explosively shed its outer layer as a supernova flash. However, if the star is exceedingly massive, it continues compressing even in the neutron stage and eventually collapses into a black hole. These stellar explosions are usually observed in other galaxies rather than our own, due to their infrequent occurrence. In fact, the last observed explosion within our galaxy dates back to the 17th century. Although it wasn't us who noticed it, astronomers back then were able to observe such an event. And in developing galaxies, there are many of them. When you look at hundreds of galaxies, now in one, now in another is happening. Here we have the Whirlpool galaxy in the Canes Venatici. Right there, you can see there's a new star. That's a supernova explosion. It's kind of not a spectacular event, so to speak, but remember, there are hundreds of billions of stars. This is the glow of hundreds of billions of ordinary stars. And this, as it lights up, rivals them all with all of them in terms of the power of radiation. So it's comparable to the glow of an entire galaxy containing hundreds of billions of stars. It unveils remarkably potent explosions, the most forceful ones ever witnessed in the universe. Can we anticipate and foresee these explosions happening in nearby stars? Yes, we can. Presently, our efforts are directed towards achieving just that. An example is Betelgeuse in Orion, which is on the brink of detonating as a supernova. In fact, it has already experienced a substantial burst. The transformation in its size is visibly evident as we observe it continuously. In contrast to most stars, Betelgeuse, along with another star, is studied not as mere points but as bodies with distinct and defined surface geography. It has expanded in size to a colossal extent, indicating its imminent rumbling. The available models provide us with an understanding of the hotspots present on its surface. This is the boiling process of her matter that we can see. This is a model, of course. It's exactly what it looks like. Let's go back. Here's this picture of Betelgeuse with large hotspots in the atmosphere. And the model shows us how convective flows of boiling mass in its interior create such colossal temperature and homogeneities on its surface. So we have a pretty accurate representation of the evolution of these stars. This is the model, and it's almost exactly the same as the actual image of the star. So keep an eye on the constellation Orion sometimes. You may be the first to witness a supernova explosion. We already know it's going to happen in the next 50,000 years. We can't be more precise because we can only see its surface. But the explosion is going to happen in the interior. If we had the capability for very sensitive neutrino telescopes and detectors, we could closely monitor the Betelgeuse core and accurately predict when its explosion will occur within mere hours. Unfortunately, we currently lack such advanced technology for neutrino detection. The explosion phenomenon in the core of a star is simulated theoretically using supercomputers, allowing us to visualize the various stages of this event. I will now present a movie that showcases a highly intricate three-dimensional model of the explosion. Watch closely as a thermonuclear reaction rapidly unfolds at the center. Although it occurs within a matter of seconds, we have slowed down the footage to display each phase in detail. Initially, the explosion appears slightly asymmetrical, causing the hotter matter to gravitate towards the section where it can easiest escape the star. This phenomenon resembles the rise of a mushroom cloud following an atomic bomb detonation, moving towards an area with lower atmospheric density. In a similar fashion, the explosion starts off-center, leading to the spillage of substance in that direction. However, due to the high temperatures, it remains trapped within the star. Eventually, you will observe the substance gathering on the opposite side of the star, at a point antipodal to the original explosion. This asymmetrical supernova explosion exemplifies this recurrent pattern. As the simulation progresses, the substance begins to converge here, forming a heated cloud. Remarkably, such asymmetric ejections from supernovae are frequently observed. The beauty of this spectacle is undeniable. It is important to note that the calculation required months of extensive supercomputer processing in order to produce these impressive visualizations. We can do it here in a few minutes. But it is a very complicated thing, because the mass of nuclear reactions and three-dimensional hydrodynamics, all of this had to be carefully calculated. Here such calculations are made, and we see that a supernova star is a rather intricate tangle of thermonuclear explosions, and more or less resembles the result of real processes. Today, Orion looks like this. This is how we see it in the Earth's sky. And when Betelgeuse explodes, it'll look like this. It's not a big deal. Well, it'll be a bright star, but it'll be about 10 times brighter than the full moon. So we won't have nights for a while. The radiation emitted during a supernova explosion is significantly stronger than that of a large solar flare. While it would be safe for us, the inhabitants of Earth near the planet's surface, astronauts in space or satellites beyond Earth would experience a noticeable increase in radiation. They would have to find a way to survive the radiation shock. However, for us, Earth dwellers, it remains safe. The radiation power gradually intensifies over a few hours during the supernova explosion, then decreases over the course of several months. Eventually, we are no longer able to see anything, although there are occasional exceptions. 1,000 years ago, a supernova exploded in the constellation of Taurus, and today, this is the result of its explosion. And here we have a remnant, a nucleus, the very last episode in the life of the core of a star that's been compressed, which is a neutron star. That's where the neutron body sits. The discovery was made by a young PhD student at Cambridge University, Jocelyn Bell, for which her supervisor Anthony Hewish won the Nobel Prize. She didn't get it. To this day, the Nobel Committee is blamed for that. But she got hers. She became a famous scientist. But the Nobel Committee passed her by. She discovered these very nuclei of exploding massive stars, neutron stars. They were discovered by their strange periodic radio emission, like beacons, spinning rapidly and sending out radio pulses. We detect them, and we called them radio pulsars. More than 2,000 radio pulsars have already been detected, and they are neutron stars. That is the most final stage in the evolution of massive stars. There are various unique ways that the life of a massive star can end. Besides white dwarfs, such as the fate of the Sun, and neutron stars, which are typically how massive stars conclude their life, there are also black holes. I'm sure you are quite familiar with black holes, as they are well known to everyone, including schoolboys. Black holes are even more massive than stars. Let me provide you with a complete overview of stellar evolution's culmination. Brown dwarfs do not transition into becoming a star at all. They bypass this phase entirely. Most stars eventually become white dwarfs, including the core of our Sun. Massive stars, on the other hand, can become neutron stars or even black holes. However, the most astronomically massive stars may erupt in such an extraordinary way that not even a black hole remains. Rather, a thermonuclear explosion disintegrates them in all directions. That's not to say this is the final picture. As long as it's a sketch of stellar evolution, there's still a lot of things we don't know, but that's probably where we should end the story.